Hey folks, in our previous video we talked about what is self-inductance, and we have a symbol for that, and it's up here. It's a capital L, okay? And we have an equation that relates the voltage of self-inductance to the rate of change of current that's happening in an inductor. And remember, an inductor is trying to keep current the same and keep magnetic flux the same, okay? It- the symbol for an inductor is a little squiggly that looks like this. Okay, so that's the symbol for inductance. Now, why is that? Well, most inductors are basically solenoids, so they look kind of like this. Um, to show you some actual pictures of inductors, uh, so here's a bunch of pictures of inductors. You'll notice that they're just coils of wire. In circuits, the coils of wire, they'll usually be put into a container like this. Um, Here, if you were to tear these apart, you would see little coils of wire in there. And here you can, for most of them, you can actually see the coils of wire. So that's basically what an inductor is. Now, you can also, there's different kinds, inductors have different purposes. So there are signal inductors, there are power inductors, there are noise suppressant inductors. They all have smiley faces like this too, obviously, because they're very happy at what they do. So anyway, but again, the main reason to have an inductor is to try to keep current the same. Okay. Now, calculating inductance, like how good is, for instance, on these pictures here, how good is this inductor versus how good is that inductor? How do you calculate what the inductance is? All right. So we kind of had these two equations. We kind of put them together, and if you equate those two, because both relate voltage, right? So what do you do here? You say negative N d magnetic flux dt equals negative L di dt. Okay. Now you notice the dt's cancel, right? And if you solve for L, the negatives drop out too. You get N times, now instead of saying d flux and di, we're just going to say flux over current. Okay, so that's the way to calculate inductance. Okay, and just like when we had capacitance, you might recall, hopefully you recall, capacitance is Q over delta V. And if you remember this equation, in the delta V there was a Q as well, and the Q is always canceled. In other words, capacitance only depended on the geometry of the object that was storing that separation of charge. Well, the same thing is true for inductance. What makes the magnetic flux? Well, it's a current. And so what's going to happen is you're going to end up with current in the numerator and denominator, and it should always cancel. And the inductance should only depend on the actual geometry of the thing that's doing the inductance. So like, how are the coils wrapped around each other? How many coils are there? What's the radius of this coil? How long is it? And so on. Okay. All right. So units. What is inductance measured in? Well, if you look at and I'll go with this last equation here. If we solve for L in this, it's E over di dt. So L, the units, the magnitude of L, is E over di dt, which would be volts per amp per second, or a volt second per amp. So technically that's what the inductance is measured in, but we have a shortcut for that. We call it a Henry, or just a capital H. Uh, it's named after Joseph Henry. Joseph Henry, along with Michael Faraday, basically discovered Faraday's law independently of each other. Faraday was the British scientist. Henry was the American scientist. Faraday got the law named after him, so Henry got this consolation prize. And this is around 1831 or so. All right, so inductance is measured in something called Henrys. Okay. Now, the symbol is this. So I've got a couple examples here. So let's do one example. Let's say that I gave you a current that was changing in the following fashion. It's a starting current and then 1 minus e to the negative some constant t. Okay, so that current is starting at 0 and increasing to a max value of I naught. All right. If I gave you the inductance, if I said here's L, okay, what is the voltage generated in the inductor by this changing current. Okay, so we know EMF is negative L di dt. Now remember, this negative is all about Lenz's law. It's just a direction thing. Okay. All right, so we got negative L times the derivative of I, which is going to be I naught times the derivative of 1 is 0 minus, and then derivative of e to the negative kt is negative k e to the negative kt. All right, now, how many negatives do we have in that? 1, 2, 3. So if you multiply them all out, you get a negative, and you get L I naught e to the negative k, k e to the negative k times t. Okay, so that would be the voltage as a function of time. Notice the voltage starts off at some max value. It's this, right? And it's negative. It's pointing the opposite way of the increasing current. It's trying to slow the current down, and it eventually dies. The voltage after a while is, if you put a big number in for time, you get 0 here. I really like this answer. Okay, hopefully you do too. All right, now let's calculate the L of a solenoid like this one here. What's the inductance of that? Okay, so L is equal to N times magnetic flux over I, right? Now, for the solenoid, and I'll kind of re-sketch this real simple. So here's our solenoid, and we'll draw like, I don't know, a couple turns there, okay? All right, so what's the inductance of that solenoid? Okay, so we have a number of turns. Magnetic flux is B times A. Now, within the solenoid, B is fairly constant, so you can just take B times A there, and then over I, okay? And you end up with an N. Now, magnetic field for a solenoid, for a few chapters ago, we figured out that was U naught number of turns per meter times I. So that's your B, and then you got the area of that solenoid, which would be pi r squared. So I'd have to give you a radius here. So there's your radius, and so that's a circle, so it's pi r squared over I. Okay, notice that the I cancels out, as it always should. And so the inductance of a solenoid is mu naught. N times N is N squared. And then you have the area, which is pi r squared, and then over L. Okay, L being the length of the solenoid. So pardon, I'm sorry, there's two L's here. You know what? I'll call, just to make it a little clearer, I'll call this cursive L, like so. And I'll make the same thing down here. So that way you don't confuse it. So L would be the length of the solenoid. Okay, so there's your inductance of a solenoid. Now notice, if you want to maximize that, what do you want to do? Well, you want to have as many turns as possible. You want to have a big area, and you want to be as short and stubby as possible. So, like if you look at some of these inductors, if you look in there, so it's many turns of wire. It's relatively short and stubby with a fairly large area. Okay, this guy is kind of medium, and in this one here, like these guys, I mean, look, they're very short and stubby with a lot of turns, right? So you'll notice that in most of these, that they're kind of short and stubby with a lot of turns. That maximizes your inductance. Okay. All right. That's basically the introduction. In our next video, we're going to start talking about how do the inductors behave when you put them in the circuits over time. I hope you found that video helpful, and thank you very much.